Greetings, the Astro 30 here, and this is the final part, part 6. It might be filmed over a couple of days, few days, but this is part 6, the final in the series of the plus minus 30 volt power supply build. And when first there was none, now I have 4. Funny thing, I came home from work yesterday and in the letterbox there was another set of them. I'm like, okay, it doesn't rain, it pours. We've got all 4 now. It's probably 6 in total. There's 2 missing somewhere. Anyhow, I'm going to use the second ones that arrived yesterday because they come in a Ziploc anti-static bag. So they're easier to get open, and these ones are in a sealed bag, so I'd have to cut them. Not that there's any problem with that, but I'm going to save these 2 modules for something else, keep them as spares, or just find a use for them eventually. Also, just for clarification, when I said in the previous video that the gain is Q1 gain times Q2 gain, and I said if this was theoretically a gain of 100 and this was a gain of 200, that would be a gain of 2000. That's actually incorrect. It's 20,000. So I just thought I'd clear that up. So I've already gone ahead and I've measured the hole centers. That's slightly warped, and that's got quite a bit of a twist in it. Anyway, I've gone ahead and already measured the hole centers, and it's 88 millimeters square all the way around the board, and the hole centers are 78 millimeters each. So 78 to there, 78 to there. So that's alright. And this is the actual circuit board. It's around about the size I thought it would be. This one does actually have a slight bow in it. I don't know if the camera can see that. Doesn't quite sit flat on the desk. You can see it's got a slight twist in that direction. I was going to say that the quality of these boards are pretty well done. It's got nice silk screen, but what let that down was the fact that it's this one's bowed. I don't know what the other one's like. Yeah, that one's got a slight bow in it too. I don't think it's the desk. No, it's not the desk. That one's got a slight twist in him too. So that's a little bit disappointing. Now I'm planning on mounting them in the enclosure side by side like that, with the AC coming in from the transformer side. So the AC socket is facing the transformers basically. The output's at the front, towards the front panel, and that puts the potentiometers on the left hand edge, or the right hand edge to you, but the left hand edge of the case. I don't know if these wires that they give you are going to be long enough to actually reach from all the way over here to the potentiometer at the front. So what I need to do is grab the case, because I want to know if I have to put in my own header pin connectors, and I don't know if I've even got enough of them, to be honest. This side will work because this one will be closest to the potentiometer, so that won't be too big of a deal. But it's this side that's going to be a bit of a issue. What I might end up doing is put these boards closer to the right hand edge, so there's like a good 70 odd mil from the side of the case here to the first board, and I'm leaving a gap in between the 2 boards for a specific reason. No, not to clear the heat sinks, but you'll see why a little later in the video. So if I look at this cable connection here, yeah, there's plenty of wire. There would have been plenty of wire if it was all the way over there. It would have made absolutely no difference to it. It would just reach just fine. So I don't have to use my own terminal connectors and make up these sodding little crimp connections, which can be a pain. However, there is a spot on here for an LED, which I am going to put a 2-pin connector, so it can run up to the 2 LEDs on the front of the power supply here. Now I will say one more thing before I assemble the board. I've seen a lot of videos on YouTube of people assembling these kits, and they're all doing one thing in common wrong. And when it comes to things like large power resistors, which can carry quite a heavy amount of current, these 1N5408s are 3 amp diodes, I believe. And power resistors like the one here, this 5 watt job. There's also a 1 watt over here. They're mounting the components flush down to the board. You shouldn't really do that. Think about the amount of current that's going to be passing through each of these devices. And of course, that means that the current passing through the device is going to be transformed into heat. And it can over time end up scorching the board. And if one of these resistors happens to fail and actually start burning up, it'll actually scorch the board. And it can make the board actually conductive in that area. So a little tip is you want to take, say, this power resistor for instance. I would mount him in the board so it's sitting up a good 3 millimeters from the board. So sort of something like that, a little bit closer maybe, so that you've got a good air gap under there. Doesn't have to be like standing up like the Eiffel Tower or the Tower Bridge in London or whatever, but you want to give it a little bit of air gap. The same with the diodes, power diodes, not so much the smaller diodes, but the ones on the bridge rectifier definitely want to prop that up because it is going to get hot. Just be aware of that. So that's just a little tip. Oh, and just one more thing, I'm only going to be using one of the regulators on this board, in other words the 24 volt regulator. Now if you remember in a previous video I said that I have a 7812 regulator, and to guess what that was for. Well, that was to replace the 7824 they've got here, so it was a 12 volt regulator, not a 24. However, looking at the data sheet of the 12 volt regulator, the maximum input voltage is 35 volts. The recommended voltage is 30. I usually don't push them any more than 28. And the 7824 maximum input voltage is 40 volt with a recommended of 35, and after rectification of the AC input it's going to be around about 33 volts to 34 volts across that IC, because this is just wired directly off of one of the bridge rectifier sections and the earth. The 12 volt regulator might be okay, but over time it won't last very long. It'll eventually internally fail, and to save that I'm going to use the original 24 volt regulator. That amp meter on there's maximum input voltage is 30 volts anyway, so 24 volt won't hurt it. Alright, about, well I think it's been about half an hour now. I've got all the mini quarter watt resistors in all these, actually probably a half watt more than anything else. Metal film resistors installed. They've drilled out these holes for the mini resistors and some of these other ones too, to 1.5 millimeter for some unknown strange reason, when you only need like a 0.1 of an 8 millimeter hole in there. So that means that it was hard to get these to stay in place whilst turning it over. You had to stick your finger over it in the end. Well, I had to anyway. And I ended up burning my finger because I held the heat onto one of the resistors too long, and then I did it again in the same place. Anyhow, would be advisable to stick it down with tape or something to hold it, but that's my only gripe, the size of the frickin' holes. You don't need large holes like that. Anyway, I'm going to move on to the other smaller components like the diodes, etc., and go from there. It appears to be 44148 diodes. I can actually read that, but I don't know what the 5.6 xenodiodes value is. So I think I'm just about to find that out. 5V1. So if you're confused as to which ones are the 1N418s and the 5 volt Zenas, well, the 5 volt Zenas has 5.1 printed on the case. If you hold it up like this, you'll see it says 5V1 on the casing, so that's how you determine that one. And always make sure that you put these in the correct way around. I'm also using up this solder that came with the other kits that I bought from JCar. Might as well use it. What I'm up to now is putting in diodes, and then I might think about putting in the 3 op-amp ICs, because it's going to be awfully difficult to do so once capacitors like electrolytic capacitors start going on the board. So that'll be what I'll be doing next. This should be a 1N4004. Yes, it is. So that goes down over here. So sometimes you've got to actually heat the joint again to make it flow a little bit better. Quite trimmed down enough. Okay, now I'll move on to the 4 power diodes. But the board's taking shape. It's starting to look like a circuit board. And I've been waiting a long time for these. And so I'm really happy that they've come. So I'll solder these in, and then I might stop recording and just get on with some final assembly. These boards are quite good to solder to, I must admit. Just be careful when trimming these off after you've just soldered them, because they are going to retain, that one was hot, a little bit of heat. Because that's what I was talking about by the reason why you prop these up. Even though I soldered this a while ago, that one is still warm. So, that's the diode. Well, that one's a little bit how you doing. It's sort of like up in the air a bit. It's matching the rest of them, but this one's sort of like So, okay, moving on to, I might do the 1 watt resistor, and well, actually no, I might stick the ICs in. Now I've got 2 of them mounted, but I ended up putting one of them in backwards, so I had to desolder it. So I'm hoping that this IC is still okay. Well, they probably should have given me IC sockets, that would have been easier. There is a notch here which denotes where pin 1 is, and there's a square pad here as well, which is where pin 1 is supposed to go. So this time I'm going to put it in the correct way round. It's kind of like putting a jigsaw puzzle together, isn't it? Yeah, putting all the final pieces in the holes. So I've bent these leads on the 0.47 ohm resistor there at a slight angle, so it allows me to keep it off the board, and when I turn it over I just let gravity hold it in after I bent the leads over at angles. I've already installed the I won't want to call them ceramic, monolithic type capacitors, all 4 of them. So I'm now doing the last 2 large resistors, which are done. I've also put the transistors in, and also soldered that IC in the correct way round. I'm actually going to put a mark on the board which one I changed around, so that I know if when I go to test it the circuit doesn't work. I've got a fair feeling I know why. Next, what I want to do is mount the, that's 2-way, mount the 2 3-pin headers for the pots. I'm pretty sure it'll be that way around, or is it the other way around? And it seems to fit the footprint better that way around. Okay, I've got my own little connector in for the LED, and and I've put the output connector in and the input connector. On the input connector, where the center tap is, it's just a blind connection that doesn't go anywhere. There's just a pad, no trace. So you can hook up a center tap transformer to this just fine. Got the variable resistor mounted in, and the two potentiometer connectors. These holes are drilled way too big because it just ended up crooked. And well, unless I actually just gently heat this and see if I can twist it like that. See, it's a little bit better. It's not as how you're doing, but yeah, the holes are drilled way too big in my opinion. They should be drilled smaller, or actually drilled for the size of the actual component that's going through the holes. So after mucking around for half an hour looking for this stupid tube of heatsink transfer comm, then I'm going to have to buy some more to smear on the back of the heatsink on the main back of that panel there, so I can get enough transfer of heat, because this is not going to be any good. Well, it's not going to be enough, I mean. I'm going to ready to mount this transistor to this heatsink, and of course I need transfer compound to do that, because the remaining parts left over does not contain any isolation material for your transistors and stuff. So it does contain, well, some bolts, and that is a threaded hole, so I don't have to worry about a nut. They give you 3-4 bolts. Looks like pretty much I'm going to be only assembling one tonight, because I really don't have the energy now. Yeah, that threads into there, so that's good. So all I need now is to find what I did with my glasses, because my eyes are getting tired as well, and I'm starting to make mistakes. It's going to put quite a fair bit on there. Might actually use the end of the tube there, spread it out a bit better. Okay, so that's that one done. So I can now turn him over and get my fingers covered in this stuff like usual, and put the screw through the transistor. And then just start it off in the heatsink. Okay, so that's the heatsink mounted in there. I can now do up this screw. Don't have to over torque it, just snug it down. There we go, that's tight enough. And then I can solder the rest of the pins. So that's the transistor mounted. I need to trim those leads down a bit because they're way too long. Okay, so what I might do now is I might mount the small electrolytic capacitors first, then I'm going to mount the regulator IC. I've forgotten to mount a connector for the fan, well, for the 24 volt. Okay, that's the first board complete. It only took me about a little over an hour and a half to do. Everything's mounted bar the transistor, wherever that's gone. The 2SD1047, I believe it is, yeah, D1047. Because that's going to mount obviously on the back panel of the power supply on the main heatsink. I've put the 24 volt regulator in on a heatsink I just had lying around. It's probably overkill for it. It's only running the module for now, that is the VA module for now, but you'll see a little later as to why I might want to put a heatsink on here. yeah, you'll see. I didn't use their crappy 2-pin connector here because I'd never find a plug that would match that, not a J-car anyway. I've just used my own, which is over here, for the output for that. And I've also put a black mark on this LED connector where the cathode is. So I know where it is. So that's that board complete, and that's basically the filming complete. Right now, I don't know whether I'm going to build the other board yet tonight, because, well, I just don't really feel like it now. This one was hard enough. I do want to get around to testing it, but yeah, I'll be up to like 3 o'clock in the morning doing it, and well, yeah, no. So I'll leave the other board for another day, probably tomorrow morning when I get up and I'm fresh. I'll assemble the next one. Won't do a video of that, it's the same as this. The only difference is there won't be the 24 volt regulator or the connector put on that board, because this is going to be the negative side of the supply. Please excuse the crudity of this diagram. I didn't have time to draw it to scale or to paint it. Anyhow, that first regulator board I showed you on the table here, that's going to be this one. This is going to be the negative side, because the voltmeter and the amp meter, or the amp meter especially, runs on the negative side of the supply. So I need to have this board as the negative regulator. So that's going to be the negative side, which is going to have the plus 24 volt on it. And the other one's not. So that board's going to be the negative side of the black binding post side of the supply. And it'll also be the one mounted closest to the front left, the inside of the case. That was the padding those other 2 modules that I got yesterday came in, not the first 2. I love bubble wrap. It's fun to mess with it. Yeah, it's still warped. So when it's screwed down to the chassis, it is going to pull it down tight, but yeah, that is putting stress on the board. But so frustrating when they can't even find a piece of material that isn't warped. I can't even think any reason behind why it would be warped. Anyway, moving on. And through the magic of editing, both boards are now complete. Well, the second one's assembled. This one only took me about an hour, and it turned out a little bit better constructed than the first one, because, well, I already knew what the pitfalls were. Now this one isn't as warped as the first one. So there's a little bit of warpage there. And that one's got a significant amount of warp. This one not so much. So yeah, that's the electronic assembly done of both boards. I'm just hoping that they work after all that effort. I'm a bit concerned about this first one because of that IC that I soldered in backwards and then had to use quite a bit of heat to unsolder it, so I hope I haven't damaged the component. I'll soon find out when I go to test it. But that's probably the good part about having a couple of spares of these. You can rob components out of the other kit and then just buy new ones later. So now I think it's time to mount these in the chassis and start wiring them up. Of course, these transistors won't be mounted to the board as previously said. They'll have fly wires going to the back of the chassis, mounted through to the back of the heatsink there, and then the wires just soldered to the board. So that's my next step, and that'll be tomorrow's little project because, well, I've got to go to work this afternoon, so I don't have time today to do it. Okay, and the day has come to finally mount these modules inside the case. I've got 2 of these 3-way PCB mount screw terminal connectors, like the one that's already on here. And that's going to be for where the power transistor mounts, so I can mount it at the back of the case, run some wires and just screw the wires down to the terminal. First of all though, however, I've got to mark out the base, the inside of the chassis here, to drill the 8 holes that are required for both boards, so I can actually mount the thing. So I'm going to do it the easy way. I'm actually going to mark it out on the underside. So there it is, all marked out there, just clears these feet. So it's going to be 4 holes here and 4 holes there. Now this should be 78 millimeters square. That doesn't look like it's 78 millimeters square. That's because it's not, it's 74 millimeters square, so I need to correct that. Okay, I was doing it in short bursts like that, so I wasn't putting so much pressure on this panel because this is only 18 gauge aluminium and it will bend very easily. So now I can change to my larger drill bit. I'm going to go about a 4mm hole. I think I'll go 4mm. That'll give me enough manoeuvrability of the circuit boards just in case one of my measurements is out or one of their measurements is out. Gives me a little bit more wiggle room. Just deburring the other side, and that's probably the easiest way if you want to save your fingers from using a drill bit by just turning around by hand. Just stick it in the end of the drill and turn the drill by hand, and then you are able to deburr it. And there it is, all mounted in. Here's the one with a regulator on it, and this is the one without. Now I can put it in the bottom panel and put the 2 screws in on either side for the final time, or the first time actually, and because it won't need to come off now. I may speak softly, but I carry a big screwdriver. And that's it. The 2 are 1. Right, so the next thing I'm going to do is I'm going to wire up the secondaries. I'm going to wire them in phase. In other words, wherever I put each of these wires, because they're marked on the transformer, into these holes, will be the same on this side. Probably doesn't matter in this sort of instance, but I'm going to keep them in phase anyway. I'm going to wire up the potentiometers. And then I'm going to power up these 2 modules for the first time and see if they actually work before I go any further. So I'm also going to have to obviously wire up the transistors. So I think the next step I'll do is I'll wire the transistors, mount them to the heatsink, screw that down with some heatsink compound. I do have a new tube of this stuff, heatsink transfer compound, a big one. I always like a big one. This is $20. It's quite expensive. So yeah, I'll just run some wires off these transistors, mount them up the back here, and with some isolators, and Bob's your auntie. Okay, now the fun begins. I've got to get heatsink compound on this and then get it on the panel and mount a transistor at the same time. The easiest way is, well, to smear it, grab a bolt, stick it through, put the nut on the other side to hold it to the panel, and then put the next transistor on, take the first bolt out, put the transistor on, straighten up the heatsink and be done. So I'm going to probably use up all this old compound. It's probably a bit too much. So this has been sitting around for God knows how long, this tube. You don't really need to cover the entire heatsink, because the area where the most heat's going to be is where the screw holes are. So I'm relatively happy with that. So as I say, I'm going to take my bolt through the heatsink, put it on the panel, grab a nut, so this will just hold it in place whilst I'm working. See, that'll just work perfectly. Then I can take my transistor and then mount it in the bottom hole first with an isolator. Get out. Why can't something be simple? Well, just looking at the transistor, it's got this isolation area already built into it. You need to still isolate this surface with the washer, but you do not need that little nylon, I think it is, bushing. So we can do it without that. This is actually the bushing anyway, and just have the insulation washer there, and that should isolate it from the heatsink. I'll test that in a minute, but we'll do it that way. Put that on. Put our isolator washer on, mount our transistor on, get our nut and try and get that started, which was easier than I thought. Get that started. It's a bit cramped in here because of the transformers in the way. We'll try and get that washer straight as possible. Now I'm going to point the transistors out at a right angle. So now I'm going to just check that this collector is isolated from, well, the screw. One on the collector, one on the screw. It is completely isolated. Now I have got some continuity. It's not very good because it's not a very good berth between the two halves, but I have got some continuity with the screw, the heatsink and the casing, but not with the collector. So the collector is completely isolated from the panel, which is what we want. Don't need to torque them up too tight, don't want to crack the silicon. Just finger tight is tight enough, and so that when you grab hold of the heatsink it doesn't rock back and forth, which it does still. So needs to be a little bit tighter. Probably would have been better having a guide screw which you could really torque down, and a bit better. That's about as tight as I want to take it. Now to make sure that both transistors are isolated from each other. Yep. Two screws obviously are not, but the two collectors are. So that's perfectly fine. That's exactly what we wanted. We wanted isolation, and that's what we got. Now I've got the fun task of routing the wires to the board. When I said to connect them here, that's the actual AC input. I meant the new connector I soldered on. So what I'm going to do is, well, this one's already short enough, so I'll be cable tying the wires together and then tying them like I did the AC wiring on the other side to the side of the case, and then we'll take it down to the board. So that's what I'm going to do next. Right, I've drawn myself a little legend. Here is the connector. Here is the crudely drawn transistor. Now the transistor would normally mount at right angles where that connector is, in that direction that it is. So what I've done is I've colour coded my wires. Brown on this pin, we'll call pin 1. Green on pin 2, which is the collector. Well, actually it could be the emitter, but whichever one of these is connected to the collector. and the blue is pin 3. So that means when I look at the connector, that's the back of the connector, that's the front of the connector. It goes blue, green, brown in that order on both modules. Alright, and that's what I've got so far. Got the thing, well, the transistors wiring table tied to the case. I've got 2 of these little self-adhesive clamp things where you can put your cable tie through and then tie the thing down to a chassis or to a sidewall or whatever, just like the one over there for the AC. And I've got them both wired up where they need to go in the correct order. So now what I need to do is connect the secondaries and wire up these 2 pots, because I'm going to do a preliminary power on test of this board before I wire anything else up, just to see whether or not I've got a working power supply or basic power supply, or whether I've got a voltage to smoke converter. Okay, that's both pots wired. I haven't shortened the leads, I'm leaving them the length they are. I'll just tie them up out the way. Now, thing is, that heat shrink doesn't serve any other purpose but to keep the wires neat. So now to mount them back in the case and hook up the secondaries and do a preliminary voltage and whatnot test. Okay, everything's hooked up. Got it plugged in. Just going to turn it on, see if nothing goes bang. Soon find out. Well, nothing went bang. I don't see any magic scope. Don't see any magic smoke escaping. So that's not getting hot. Our output heatsink is cool still. So is each transistor. Alright, I'm just going to do a DC voltage measurement across the bridge rectifier. We have 34.3 volts on that module. The leads are around the wrong way around. We have 34.4 on the second one. Alright, I've just got some fly leads connected to the output of the first module, and I can see that the voltage is increasing. So now I've got 12.2 volts on that module and 29.7 at maximum. And both transistors are still nice and cold. I'll wind the current all the way up. They're still nice and cold. So I'll set the current about half. Turn that back down, and I'll do the same for the second module. Okay, now the second module is connected. We wind up the voltage and we have an increase in voltage. 14, 16, 18, 21, 32.4. There's a bit of an imbalance here. The other one was, what, 29.7? This one is 32.4. Well, that could be due to tolerances in the components chosen, I suppose. Yeah, or just, you know, one of those things. But the transistor is nice and cold. Well, it's not drawing any current yet. So I know that there's no parasitic current draw on the output. Nothing's shorted, so it's not drawing heaps of current. The transistors are nice and cold. The driver transistor for the Darlington, not even really warm. Okay, so now I can move on to the next step, which is wiring all the internals. So whilst I've got these connected, I should just do the 0 volt adjustment. So we're about 5 millivolts, 4, 3, 2, 1, 0. Negative. So now, if I wind it back up a bit, we are at 0, that's calibrated. So if I go back to that scale, higher scale, and see what the output voltage is doing, 32.4. Okay, now I'll zero out the second one. So at the moment we've got 13 millivolts, so I need to turn that down. So 5, 3, 2, 1, 0. And there, ooh, just not quite right. there it is there, 0 millivolts. So again, the output is 29.7, so there's like 2 volt difference between the two modules, which is okay. There's no issue with that. It doesn't have to be exactly precise. Now, as you can see, the wiring is pretty messy. I'll just turn that off now. The wiring is pretty messy with the AC mains and stuff. I'm going to tidy it all up, and I can disconnect my test leads. Okay, now comes the fun part of wiring up the 2 modules together to the output and the VA meter. As if you remember, this is 1 negative of the first module is connected to the positive of the second module to form the 0 volt rail. Now switch 2 here is your meter range switch. This wire means the yellow wire, the thin yellow wire on the VA meter. So that's being switched between either the 0 volt rail or the positive rail. And notice now there's a switch here on the output, switch 3. You've got your voltmeter and your ammeter here, the big black wire going into the negative of the module, 24 volt powering it, and then the red forms the output to the negative post. But there's a switch now here. This switch, switch 3, which is a dual pole, dual throw, is the load switch. So you can switch the load on and off, but you still want your voltage meter in series, well in circuit with this, so you can do your voltage adjustment on your power supply before applying it to the load. So you can double check and triple check that you got the right voltage, everything's connected right, then you flip the switch. However, there's just one issue with this. There's going to be 3 amps flowing through this circuit, theoretically speaking. Not all the time, but in some cases. Now, let's just have a look at something. Now this was going to be my load switch. This is a DB-DT, dual pole, dual throw. It's rated at 2 amps at 250 volt, 3 amps at 117 I think it is, or 175, I can't remember off the top of my head. But I don't really want to run 3 amps through those contacts. So I had a thought about that, and now why I'm leaving a space between these boards will become quite clear. I've got a 24 volt 10 amp at the contacts relay. That's 10 amps DC. So all I need to do is connect up a SPDT or SPST switch from the 24 volt rail coming off of the first module to power it, and it goes through the switch, comes back into the relay. You just turn the relay on and off with a protection diode or flyback diode across the coil, obviously, so when the coil de-energizes it doesn't send a spike of 500 volts back up into the regulator and killing it. Now then I can just wire my load across these pins back to the sockets. It's coming together. I'm quite pleased with how things are going. So all I need to do now is just do the final piece of the puzzle, which is the internal wiring, including to the binding posts here, and yeah, see if we've actually got a working power supply when we put it under load. Okay, we've got some progress happening here. I've got the LEDs for the current limiting wired up. I've changed that DP-DT switch to an SPDT, and I've put my positive 24 volt wire coming off of the negative module in here, and also the positive wire to the VA meter. And I've got my 2 negatives, well 1 negative at least at the moment, down here, and the other one's floating around. I think that's that one there, yeah. And I've just got the relay sitting there. Now I've got across that relay coil a 1N5819. It can just as easily be a 1N4001. It's just to suppress the back EMF when the coil field collapses, which can send a spike up to 500 volts back up through the regulator, which you don't want to do. So where the cathode is on this diode is where the positive connects. In actual fact, it'd probably be easier to draw a diagram. Okay, so we've got a negative regulator which goes into a power transformer. So that's the AC side. We have its positive and negative outputs. We also have a plus 24 volt rail coming out. So I've got that there connected to a switch like so, which is then going to be going into a relay coil across this negative point here. That's our relay, so that's, and that is going to be switching, in the case of the negative regulator's case, it's going to be switching the negative output, and so that's part of that. And we've got this diode connected the wrong way around. Let's try that again. See, I make mistakes. And we've got this diode connected like that. So it's reverse biased, obviously, so it's not allowing your positive voltage to go into the negative and short the thing out. So all that does is when this relay turns off and the field collapses, it will attempt, because of the flow of current, it will attempt to sink it back to the negative, and that's exactly where you want it to be sinking it to, because usually negative is supposed to be earthed anyway. But that's the theory behind it. All that does is it removes the spike that this relay coil will present to whatever is driving it. In this case, a regulator. It could be a a transistor that's turning the relay on and off. You definitely need one of these in there, because you'll eventually sink all the voltage spike and current through the transistor, which won't make the transistor very happy or last very long. So you may be asking yourselves a very valid question. How am I going to mount this relay? Am I going to stop it from flopping around? Well, I'm just going to hot glue it to the chassis. You've got to be relatively quick with this. So yeah, that's glued in. So that's glued in. So just for good measure, it's a bit crooked, but just for good measure, I'm going to apply a little bit more hot glue on two of the edges. And just for good measure, I'm going to put some on the LEDs to stop them coming back out the other way, or pushing the LED out. Don't need much on there, just a little bit. Don't know if I'm going to be able to get to that bottom one or not. Probably not. Not at the same. Oh, I might just be able to get in there. I totally missed. So yeah, there's a nice glob of hot snow down the bottom there. Okay, so what's left to wire is the relay coil, and put another wire back to the switch to turn it on and off, and also attach both these negative leads together over here at the anode of the diode. And then we'll come back after that. Okay, moment of truth. I've got the relay wired in now. That went slightly crooked. Now we'll see if the load on-off switch works. And I can see that the display is also working as well, so that's good. Yep. The relay's working. As we can see, the display lights up, so I know that that's still working. What I'm not impressed with is, though, this connector is awfully loose. So is the circuit board, it's just roaming about. This connect down here is fine, but this one is our current sense pins. Yeah, the actual plug is loose in the socket. So I'm hoping I've still got a connection. So I'll just put my meter across this current sense, and I should have almost close to 1 ohm, which I do, 0.8, and if I move the connector back and forth, it's not changing or losing connection, so that's perfectly fine. Well, that be all the wiring done. Got the outputs wired to the relay, the two commons together, one negative of one regulator with the positive of the other regulator. and I've got the range switch wired up. So now it's time to plug it in and turn on. I've still got to tie these wires up a bit and see whether or not I've made a variable bench supply or one of those voltage to magic smoke converters. Okay, moment of truth. Well, it appears to be working, and I've got 63 volts across the meter here, because it's wired across the positive of one module to the negative of the other. That's the load switch. Now it's measuring only between one of the modules, which is this module here, so it's saying 30.1 volt. How accurate is that scale? Well, let's find out. I've got 29.7 there, so that voltage reading is about probably, I don't know, 0.3 of a volt out. I'm not really fussed about that. Now as for across the whole entire thing, I've got 62.8 there, and I've got 62.1 there. So it's about 4 millivolt error between both boards. 4 millivolt on one, 4 millivolt on the second. So I know that that's working. Now let's do a current test. Alright, so I got this 10 watt, 10 ohm resistor, and what I'm going to do now is I'm going to connect it across the negative and positive binding posts here. So push that back a bit. So load is off, connect that to there. I'm going to set this to 10 volt roughly. That's close enough. Now that 10 volts should be going across this resistor. Might help if I actually connected the right fly lead. Okay, now we've got 2 amps of current draw at 10 volt there. That's going to get red hot. Well, yeah, well it's not anyway. So now I'm just testing current limiting. That just kicked in on both modules now. So yeah, we're getting current limit now. So I know I can limit this current to 1 amp, roughly 1 amp. And you'll notice that the voltage has now dropped to 5.5 volts at 1 amp. That's exactly what constant current is supposed to do. Now I'll just, yeah, those transistors are getting quite hot. Thing is, it is passing it to the heatsink, but they themselves are red hot. So I know that they're getting fairly hot. I'm not sure if it's actually transferring the heat correctly into the heatsink, but the heatsink is getting warm, I can feel it. So I know at 1 amp that's getting quite hot. And that's only putting in, like, you know, 5.5 volts. And they're very hot to the touch. But it is actually sinking it through into the heatsink, because the heatsink is actually getting hot. So the heatsink is doing something. So you just can't keep touching that. Okay, so we have no current limit. We get 2 amps. And they're very hot to the touch. But anyway, it's working. I might have to keep an eye on that back there. I can actually feel the heat in that panel. The panel's not much any hotter than the heatsink. It's just the device itself is getting very hot. But it is sinking the heat into the heatsink, so it'd probably be alright. I mean, These transistors should be able to run 160 degrees Celsius. That wasn't even boiling point yet. I just couldn't put my fingers on it for too long. So let's up the voltage, and see what current draw we get across this resistor now. That's red hot. Oh, 3.9 amps. That's quite a considerable amount of power. So I know that this thing is capable of delivering 3.9 amps. At risk of blowing myself up, let's try it 30 volt. That's only across here and here. I'd hate to see what it is at full voltage. 5 amps. Okay. So it is working, and the way I wanted it to work is working the way I wanted it to work. So I've tested it now, and I know that it's going to work, and that resistor will be hot still. Yeah, that's boiling. So I now know that this power supply is working the way it should do. I can now tidy up these wires and zip tie them together and put the lid on. Okay, there it is, lid on. I'm finally happy to see this project complete, and I thank everybody for following me along on this journey. I hope you enjoyed it. This is going to be a fun video to edit now. So anyway, I'm the Astro 30. If you like this video, please remember to rate, comment and subscribe below, and you can always follow me on Facebook and Twitter. I always like new likes on Facebook, and as always, this is the Astro 30 saying, see ya, have a great day.